When we think about aircraft, our imagination conjures familiar passenger airliners or military fighters humming in the sky thanks to aviation fuel. But in the mid-20th century, engineers and military personnel from the United States and Soviet Union conceived something far more ambitious: aircraft that would run on nuclear energy. Such machines were called atomic aircraft. Why does the idea of airplanes with nuclear reactors on board evoke mixed feelings in people, from fascination to anxiety? Let's explore where this concept came from, how it relates to other nuclear technologies, and why atomic aircraft never became part of our everyday lives. The very idea of atomic aircraft was born in an era when nuclear energy was considered the key to the future. In the 1940s and 1950s, humanity was just beginning to harness the power of the atom. Nuclear power plants were still a distant dream, but nuclear reactors were already appearing on submarines and icebreakers. These technologies seemed like real breakthroughs. Ships could spend months at sea without needing refueling. If nuclear energy could propel enormous vessels across oceans, why not apply it to aircraft? The vision of an airplane that could fly for weeks without landing was enticing, especially for the military. At that time, the Cold War between the USA and USSR was intensifying, and both sides were seeking new ways to gain an advantage. Why did atomic aircraft cause anxiety? The issue wasn't just the complexity of the technology, but also that a nuclear reactor aboard an aircraft is a potential danger. If icebreakers or submarines suffer accidents, the consequences are limited to the sea. But an aircraft with a reactor that crashes to the ground could become a source of radioactive contamination for entire regions. This fear became one of the reasons why atomic aircraft remained more of an experiment than reality. However, in the mid-20th century, such concerns took a backseat to the ambitions of superpowers. The USA and USSR saw atomic aircraft not just as transportation, but as strategic weapons capable of changing the rules of the game. In the USA, the idea of atomic aircraft emerged immediately after World War II. The end of the war with Japan in 1945 coincided with the beginning of the arms race. American military leaders realized that conventional aircraft, which required enormous amounts of fuel, could not effectively carry out intercontinental missions. Missiles of that time also had limited range. How could nuclear weapons be delivered to potential enemy territory under such conditions? The answer came quickly. They needed to create an aircraft powered by nuclear energy. Such an aircraft could fly for extraordinarily long periods without refueling, making it ideal for bombing or reconnaissance. In the Soviet Union, they arrived at a similar idea somewhat later, but with no less enthusiasm. Interestingly, public perception of atomic aircraft differed from other nuclear technologies. Nuclear icebreakers, such as the Soviet Lenin, or submarines like the American USS Nautilus, were perceived as engineering marvels. They didn't cause panic because their operations took place far from populated areas. But an aircraft with a nuclear reactor flying over cities or villages seemed far more dangerous to people. And this wasn't surprising. An accident involving such an aircraft could have catastrophic consequences. However, engineers and military personnel saw atomic aircraft not as a threat, but as an opportunity. They believed that nuclear energy could make aviation limitless in flight range. To understand why atomic aircraft never became reality, we need to delve into the history of their creation. Both the USA and USSR invested enormous resources in these projects, creating prototypes and conducting tests. The Americans started earlier, in the 1940s, when the Pentagon announced a competition to develop an aircraft with a nuclear engine. The Soviet Union joined the race in 1955, involving leading design bureaus. Both countries created flying laboratories that tested the impact of nuclear reactors on crew and onboard systems. These experiments proved complex, expensive, and dangerous, but they left an interesting trace in the history of aviation. In the following parts, we will examine in detail how the USA and USSR attempted to bring the idea of atomic aircraft to life. We will discuss American projects such as the Convair YB-60 and NB-36H, as well as Soviet developments, including the Tu-95LAL and projects from the Myasishchev and Antonov design bureaus. Each of these stages shows how engineers struggled with technological challenges while military leaders tried to find a balance between ambitions and safety. But first, let's dive into the American part of the story, which began immediately after World War II. After the end of World War II, the United States found itself on the threshold of a new era. The Cold War was just beginning, and the Pentagon was searching for ways to ensure military superiority over potential adversaries. One of the main problems of aviation at that time was limited flight range. Conventional aircraft running on aviation fuel required enormous fuel reserves for intercontinental missions, while missiles could not yet cover great distances. In 1945, when the ink on Japan's surrender document had barely dried, American military officials announced a competition to create an aircraft with a nuclear engine. The idea was simple but ambitious. An aircraft that could fly for practically unlimited time would become an ideal instrument for strategic bombing or reconnaissance. Thus began the American Atomic Aircraft Program. The main reason the Pentagon became interested in nuclear engines was the need for aircraft capable of performing intercontinental missions without refueling. At that time, the USA was preparing for possible confrontation with the Soviet Union, and military strategists wanted to have an instrument that would allow delivering nuclear weapons over long distances or conducting prolonged aerial reconnaissance. Conventional aircraft such as B-29 bombers had already demonstrated their effectiveness during the war, but their dependence on fuel limited their capabilities. Missiles, which were just beginning to be developed, also could not provide the necessary range and accuracy. A nuclear engine seemed like the perfect solution. It could provide an aircraft with energy for weeks or even months of flight, which would change the rules of the game in military aviation. The first steps in implementing this idea were taken by General Electric. In the mid-1950s, the company's engineers developed a simplified nuclear engine that was to become the foundation for atomic aircraft. Its design was relatively simple, but had serious flaws. Air entering through the intake passed directly through the reactor's active zone. There it was heated, cooling the reactor, and then directed to the turbine blades and expelled through the nozzle, creating thrust. Such an engine was called direct cycle, and it had one key feature. It could only be started when the aircraft was already moving through the air. This meant that conventional engines were needed for takeoff, and the nuclear reactor was turned on only at a certain altitude. But the main problem was radiation. The contrail of an aircraft with such an engine literally glowed, meaning it was radioactive, making it dangerous for anyone who found themselves near the flight path. This General Electric engine was a real engineering challenge. On one hand, it was significantly lighter than traditional nuclear reactors, making it suitable for aviation. But the simplification led to compromises. The reactor's active zone was open, and the air passing through it became radioactive. This created enormous risks not only for the crew, but also for ground personnel and populations in areas over which the aircraft flew. Engineers tried to minimize these risks, but 1950s technology did not allow for creating an effective radiation protection system. Despite this, the Americans decided the idea was worth testing and proceeded to practical experiments. For testing the nuclear engine, the B-36 bomber was chosen and modified for the program's needs. Why specifically the B-36? This aircraft had already proven itself as a strategic bomber capable of carrying heavy armament, including nuclear bombs. It was developed during the war for possible raids on Japan, including Tokyo, making it perfect for the Pentagon's ambitious plans. The modified version received the name Convair YB-60 Peacemaker. The name sounds ironic since the aircraft's main task was to deliver nuclear weapons to targets in enemy territory, such as regions of the Soviet Union, including the Donbass. To adapt the B-36 to the nuclear engine, engineers faced a number of challenges. One of the main ones was reactor cooling. It turned out that the air passing through the active zone could not provide sufficient cooling. To solve this problem, water cooling based on a boron solution was added to the system. Boron is known for its ability to absorb neutrons, which help control the nuclear reaction. The reactor was placed in the aircraft's rear cargo compartment to maximize its distance from the crew. Additional shields were installed to protect the pilots, but as practice showed, this did not provide an adequate level of safety. Radiation remained a serious threat, and even in the rear of the aircraft, the crew was insufficiently protected. The development of the YB-60 became the first real step toward creating atomic aircraft, but it revealed countless problems. The nuclear engine was not only dangerous due to radiation, but also cumbersome and complex to use. Moreover, the aircraft itself flew far from perfectly. Its flight characteristics left much to be desired, which forced engineers and military personnel to think, was it worth continuing work in this direction? The Convair YB-60 Peacemaker became the first real embodiment of the atomic aircraft idea in the United States. This modified B-36 bomber, chosen for nuclear engine testing, was meant to become a symbol of U.S. technological superiority in the Cold War. Its development was a logical continuation of the Pentagon's ambitions to create an aircraft capable of performing intercontinental missions without refueling. However, as practice showed, reality turned out to be much more complex than plans on paper. Let's examine how this peacemaker was designed, what engineering solutions were applied, and why it failed to meet expectations. The YB-60 was created based on the B-36 strategic bomber, which had already proven itself as a reliable machine for long-distance flights. This aircraft was developed during World War II for raids on Japan, particularly Tokyo, so it had a large cargo bay and could carry heavy armament, including nuclear bombs. The aircraft's weight reached 130 tons, making it an ideal candidate for nuclear reactor installation. However, adapting such complex technology to aviation required unconventional solutions, and engineers encountered a series of problems that ultimately determined the project's fate. The nuclear engine, developed by General Electric, was a key element of the YB-60. Its design was based on the ramjet principle. Air entering through the intake passed through the reactor's active zone, was heated and directed to the turbine, creating thrust. But this process had a serious flaw. The air that contacted the reactor became radioactive, and the aircraft's contrail literally glowed. This meant that every flight left behind a trail of radiation that posed a threat to anyone nearby. This characteristic made the YB-60 not only dangerous for the crew, but also potentially catastrophic in case of an accident. To make the engine suitable for aviation, General Electric engineers simplified its design as much as possible. They created a lighter reactor than those used on submarines or icebreakers, but this simplification led to new problems. One of them was cooling. It turned out that airflow was insufficient for effective cooling of the reactor's active zone. To solve this problem, water cooling based on a boron solution was added to the system. Boron absorbed neutrons, helping to control the nuclear reaction and reduce the risk of uncontrolled heating. But even with this system, the reactor remained bulky and difficult to manage. Another important aspect was crew safety. The nuclear reactor was placed in the aircraft's rear cargo bay to maximize its distance from the pilot's cabin. Additional screens were installed to protect the crew by blocking radiation. However, these measures proved insufficient. The level of protection was minimal, and pilots still experienced radiation exposure during flights. This created serious health risks, as prolonged radiation exposure could lead to severe consequences such as radiation sickness or cancer. Engineers tried to optimize the design, but 1950s technology did not allow for creating effective protection that would guarantee safety. Despite all efforts, the YB-60's flight characteristics left much to be desired. The aircraft was heavy and unwieldy, and the nuclear engine did not add maneuverability or speed. The ramjet system, though innovative, could not provide stable operation under various flight conditions. For example, the engine could only be started in flight, meaning additional conventional engines were needed for takeoff and landing. This complicated the aircraft's design and made it less practical. Additionally, the radioactive exhaust created problems not only for the crew, but also for ground personnel who had to service the aircraft after flights. The Pentagon hoped that the YB-60 would become a breakthrough in military aviation. The aircraft was supposed to perform strategic missions such as delivering nuclear weapons to distant targets, for example, to industrial regions of the Soviet Union. But reality proved different. Poor flight characteristics, high risks of radiation contamination, and maintenance complexity made the YB-60 more of an experimental project than a practical solution. American military officials and engineers quickly realized that the ramjet nuclear engine was not the path that would lead to creating an effective atomic aircraft. These failures forced the Pentagon to reconsider its approach to the program. Instead of continuing to improve nuclear engines to enhance flight characteristics, the Americans decided to take a different path. They focused on creating a flying laboratory that would allow studying the impact of a nuclear reactor on the aircraft and crew without relying on it as a source of thrust. This led to the next stage of the program, the NB-36H Crusader aircraft, which we will discuss in the next part. But already from the YB-60 example, it became clear that the path to creating an atomic aircraft would be much more complex than initially imagined. After the failure of the Convair YB-60 Peacemaker, American engineers and military officials realized that creating an aircraft with a nuclear engine that could effectively fly and perform combat missions would require significantly more time and resources. Problems with flight characteristics, radiation safety, and design complexity forced the Pentagon to change its approach. Instead of immediately improving the nuclear engine, the Americans decided to focus on studying the impact of a nuclear reactor on aircraft and crew. This led to the creation of the NB-36H Crusader, a flying laboratory that became a unique experiment in aviation history. Let's examine how this aircraft was designed, what it was used for, and what conclusions were drawn from the test results. The NB-36H Crusader, like its predecessor, the YB-60, was based on the B-36 bomber. This aircraft was chosen for its size and ability to carry heavy equipment, as the nuclear reactor, even in simplified form, remained bulky. However, unlike the YB-60, where the reactor was part of the propulsion system, in the NB-36H, the nuclear installation had a completely different role. It was completely disconnected from the aircraft's engines and did not affect flight. The 1-megawatt reactor was installed solely to study how radiation affects onboard systems, crew, and the aircraft structure itself. Essentially, the NB-36H was a flying testbed for nuclear technology under aviation conditions. The name Crusader sounds heroic, but the aircraft's mission was quite mundane. It was meant to help engineers understand whether it was possible to safely place a nuclear reactor aboard an aircraft. The main focus was on two questions: how to protect the crew from radiation, and what would happen to the aircraft if the reactor operated during flight. For this purpose, the NB-36H was equipped with special sensors that recorded radiation levels in different parts of the aircraft, as well as systems for monitoring reactor operation. The reactor itself was placed in the rear section of the aircraft, away from the pilot's cabin, but as with the YB-60, crew protection remained inadequate. The shields designed to block radiation could not completely eliminate its effects. NB-36H testing was conducted with particular caution. The Americans were well aware of the risks associated with flying an aircraft with a nuclear reactor on board. One of the greatest fears was related to a possible accident. If the NB-36H had crashed, radioactive debris could have caused serious contamination. To minimize these risks, each flight was accompanied by a second B-36 that served as backup. This escort aircraft was loaded with measuring equipment to monitor the radiation background around the NB-36H. Additionally, a squad of Marines was on board. Their task in case of an accident was to immediately parachute to the crash site, surround the wreckage, and guard it from outsiders, whether local farmers, journalists, or, as the Americans joked, KGB agents. The NB-36H completed 47 flights, each of which was part of a carefully planned experiment. During these flights, engineers collected data on how radiation affected electronics, aircraft materials, and crew health. Special attention was paid to pilots and crew members who remained in the cabin. Although precise data on their health condition is unavailable, it can be assumed that prolonged radiation exposure did not pass without consequences. The text mentions jokes about the glowing bald heads of pilots and Marines, hinting at possible effects of radiation exposure, such as hair loss or more serious health problems. These side effects likely became one of the key factors that influenced the program's future. The NB-36H test results proved disappointing. Engineers concluded that the technology of the time did not allow for the creation of a safe atomic aircraft. Crew protection from radiation remained insufficient, and the risk of an accident with a nuclear reactor on board was too high. Even if the aircraft didn't crash, its operation posed a threat to ground personnel and populations in areas it flew over. The radiation background from the reactor, though minimized through shielding, was still dangerous. Moreover, the reactor itself, disconnected from the propulsion system, provided no practical benefit to flight, making it more of a burden than an advantage. These conclusions forced the Pentagon to reconsider the prospects of atomic aircraft. The NB-36H showed that the idea of an aircraft with a nuclear reactor was theoretically possible, but its implementation required technological breakthroughs that simply didn't exist in the 1950s. Safety problems, design complexity, and the lack of tangible advantages compared to conventional aircraft put an end to further experiments with nuclear engines in the United States. Instead of continuing development, the Americans focused on other directions, such as improving refueling aircraft and rocket technologies. The NB-36H Crusader became an important stage in the history of atomic aircraft, but not in the sense its creators had hoped. It did not lead to the creation of a nuclear-powered combat aircraft, but rather showed the limits of the technology of that time. This aircraft remained a flying laboratory that helped gather valuable data, but did not bring humanity closer to the era of atomic aviation. Meanwhile, on the other side of the ocean, the Soviet Union was just beginning its experiments with atomic aircraft, and their approach was somewhat different. While the Americans were conducting their nuclear aircraft experiments, the Soviet Union did not stand aside. Although the USSR joined the nuclear aviation race later in 1955, it approached the matter with characteristic thoroughness. In the Soviet Union, the idea of aircraft with nuclear reactors was perceived as strategically important, as the Cold War demanded new technologies to maintain parity with the United States. Leading design bureaus were involved in implementing this ambitious project. Tupolev Design Bureau, Myasishchev OKB, Lyulka OKB, and Samara Plant No. 2. The first notable result of their work was the Tu-95LAL flying laboratory, created based on the Tu-95 strategic bomber. Let's examine how Soviet engineers approached creating nuclear aircraft, how their approach differed from the American one, and what results these experiments brought. The Soviet nuclear aircraft program started with a 10-year delay compared to the USA, but this allowed engineers to take into account some lessons from their American colleagues. Instead of immediately creating a combat aircraft with a nuclear engine, the USSR decided to take the testing path similar to the American NB-36H. The Tu-95LAL flying laboratory was to become a platform for studying the impact of a nuclear reactor on the aircraft and crew. Unlike the Americans, who gave their aircraft resounding names like Peacemaker or Crusader, Soviet engineers were more pragmatic. Their aircraft received the simple name Tu-95LAL, Flying Atomic Laboratory. No pathos, just a clear designation of purpose. The Tu-95, chosen for the experiments, was one of the most reliable strategic bombers of the USSR. Its powerful turboprop engines and long flight range made it ideal for testing nuclear installations. Unlike the American NB-36H, where the reactor was disconnected from the power system, Soviet engineers went further and installed a dual-circuit nuclear reactor on the Tu-95LAL. This was a key difference. In the dual-circuit system, the reactor's active zone did not contact the external environment, which significantly reduced the risk of radioactive contamination. The reactor was cooled by liquid sodium, which transferred heat to water in a boiler. The generated steam could theoretically drive a turbine that would power electric motors rotating the aircraft's propellers. Such a design was much more complex than the American direct cycle engine, which simply passed air through the active zone. The Soviet approach had several advantages. First, the dual-circuit system was safer, as radioactive elements remained isolated from the external environment. This reduced the risk of radiation release into the atmosphere, which was a serious problem in the American YB-60. Second, liquid sodium as a coolant allowed more efficient reactor temperature control, which was critically important for its stable operation in flight. Theoretically, if the reactor were connected to the power plant, it could provide the aircraft with energy for long flights. But at the testing stage, the Tu-95LAL reactor, like in the American NB-36H, did not participate in aircraft propulsion. Its task was to test the impact of radiation on onboard systems and crew. The Tu-95LAL made 34 flights, and each was part of a careful experiment. Engineers focused on assessing how radiation affects electronics, aircraft materials, and pilot health. Shields were used to protect the crew, designed to block radiation, but as in American experiments, complete safety could not be achieved. Soviet engineers tried to improve protection, but the technologies of that time had their limits. Despite this, the tests showed that with proper shielding, a nuclear reactor could theoretically be installed on an aircraft without catastrophic consequences for the crew. This was an important result, as it confirmed the possibility of further nuclear aircraft development. However, the Tu-95LAL program did not go beyond the experimental phase. After 34 successful flights, the aircraft was dismantled, the nuclear installation removed, and the Tu-95LAL itself was sent for scrap metal. Why did this happen? First, although the tests proved the theoretical possibility of using a nuclear reactor in aviation, practical implementation required enormous resources. The dual-circuit reactor was complex and expensive, and its integration into the power plant required additional engineering solutions. Second, Soviet military officials, like their American colleagues, began to realize that other technologies, such as tanker aircraft and intercontinental missiles, were developing faster and were more economically justified. The Tu-95 LAL became an important step in the Soviet nuclear aircraft program, but it remained only a flying laboratory. Soviet engineers showed that their approach to nuclear technology was more thoughtful than the American one, thanks to the use of the dual-circuit system. But even this could not overcome the main obstacles: the complexity of radiation protection, high cost, and the emergence of alternative solutions. In the next part, we will examine how the USSR tried to go further, developing projects Tu-119 M60 and M30, which remained only on paper. After the experiments with the Tu-95 LAL flying laboratory, the Soviet Union did not stop at what had been achieved and continued working on the idea of nuclear aircraft. Although the Tu-95 LAL proved that a nuclear reactor could theoretically be installed on an aircraft, the practical application of such technology remained a challenge. Soviet design bureaus, particularly Tupolev's KB and Myasishchov's OKB, proposed several ambitious projects that were meant to take nuclear aviation to a new level. Among them were the Tu-119 M60 and M30, aircraft that remained at the drawing board stage or in early development. Let's examine what these projects were like, what ideas the engineers proposed, and why none of them reached realization. First on the list was the Tu-119, which was also based on the proven Tu-95 bomber platform. Unlike the Tu-95 LAL, where the nuclear reactor was used only for testing, the Tu-119 planned to integrate an advanced reactor into the aircraft's power plant. The idea was for nuclear energy to directly drive turbines that would rotate propellers through electric motors. This was an ambitious plan, as it required not only creating a reliable reactor but also developing an energy transmission system that would ensure stable operation in flight. Soviet engineers hoped that the dual-circuit system, already tested on the Tu-95 LAL, would become the foundation for this project. Liquid sodium as a coolant was to provide efficient cooling and heat transfer, while shielding of the reactor core was to reduce radiation risks. However, the Tu-119 never left the drawing board. Development required significant resources, and the technologies of that time did not allow for creating a compact and safe reactor that would meet aviation requirements. Additionally, the economic feasibility of the project was questionable. Even if the Tu-119 had been successfully built, its operation would have been too expensive, and the risks associated with radiation remained high. Ultimately, the project was frozen, and the Tu-119 remained only a concept that showed how difficult it was to transition from experiments to creating a full-fledged nuclear aircraft. Myasishchov's OKB approached nuclear aircraft creation with more radical ideas. Their M60 project was based on the M50 bomber and envisioned installing 4 nuclear turbojet engines operating on an open cycle, similar to the American engine from General Electric. In such a system, air passed through the reactor's active zone, was heated, and created thrust. This was simpler than a dual-circuit system, but, like with the Americans, created the problem of radioactive exhaust. This approach was cheaper but significantly more dangerous, as each flight would leave behind a trail of radiation. One of the main problems with the M60 was crew safety. To protect pilots from radiation, Myasishchov's OKB engineers proposed several unusual solutions. Initially, they developed a concept for a cabin in the form of a thick-walled capsule without windows. Pilots were supposed to navigate using a periscope and radars, making aircraft control extremely difficult. This idea was so impractical that it was quickly abandoned. Then came a proposal to create an unmanned version of the M60. Drones in the 1950s were still in early stages of development, and technology did not allow for realizing such a complex machine. Finally, in desperation, the designers proposed recruiting pre-retirement age pilots for flights. The idea was that radiation exposure would have fewer long-term consequences for them due to their age. This proposal was probably a joke or an extreme manifestation of desperation, but it vividly illustrates how difficult it was to solve the radiation protection problem. All these ideas, from windowless capsules to pensioner pilots, show that Myasishchov's OKB was trying to find some way to make the M60 viable. But each solution only emphasized the project's shortcomings: complexity, danger, and high cost. Ultimately, the M60 remained on paper, never even reaching the prototype stage. Near the end of the USSR's existence, Myasishchov's OKB made one more attempt, the M30 project. This aircraft was supposed to be significantly more advanced and safer. It was planned to install 6 nuclear turbojet engines operating on a closed cycle. In such a system, heat from the reactor to the engines was transferred through a coolant, liquid lithium and sodium. This allowed isolating the reactor's active zone from the external environment, significantly reducing the risk of radiation contamination. Additionally, the engines were to use aviation kerosene for additional efficiency, making the M30 a hybrid system. The M30 looked more promising than the M60 as it took into account lessons from previous projects. The closed cycle reduced radiation risks, and the hybrid design could increase energy efficiency. Moreover, engineers paid more attention to the safety of ground personnel and pilots, trying to develop better shields for radiation protection. But even these improvements could not save the project. The M30 proved too expensive and complex to implement. During the economic difficulties of the late 1980s, the USSR could not afford to invest huge amounts in experimental aviation, especially when alternatives such as missiles and tanker aircraft had already proven their effectiveness. All 3 projects, Tu-119, M60, and M30, became examples of how ambitions collided with real limitations. The Tu-119 showed that integrating a nuclear reactor into a power plant was theoretically possible, but too complex in practice. The M60 illustrated how far engineers could go in attempts to solve the radiation problem, even proposing absurd ideas. The M30 was a step forward, but its appearance coincided with a time when nuclear aircraft had already lost relevance. In the next part, we will examine the USSR's last attempt to create a nuclear aircraft, the Antonov Design Bureau project based on the An-22, which was to become an anti-submarine aircraft with a nuclear engine. While the Tu-119, M60, and M30 projects remained on paper, the Soviet Union did not cease its search for ways to apply nuclear energy in aviation. One of the last and most interesting experiments in this field was the development by the Antonov Design Bureau, aimed at creating an anti-submarine aircraft with a nuclear power plant. This project was based on the An-22 anti-transport aircraft and aimed to provide long-duration patrolling of maritime areas for submarine detection. Let's examine how Soviet engineers attempted to realize this idea, what challenges confronted them, and why this project, despite certain successes, never reached serial production. The Antonov Design Bureau received a task from the Soviet military to develop an aircraft that could remain airborne for several days without refueling. Anti-submarine aviation required a special approach. Aircraft had to patrol vast maritime territories, searching for enemy submarines, which was particularly relevant during the height of the Cold War. Conventional aircraft, even with refueling, could not provide such flight duration. A nuclear reactor seemed like an ideal solution, as it could power the engines for dozens of hours, allowing the aircraft to remain in the patrol zone much longer than any other machine of that time. For the project's implementation, they chose the An-22 Ante, one of the world's largest transport aircraft, renowned for its cargo capacity and reliability. The An-22 had already proven itself as a versatile platform capable of carrying heavy equipment, making it ideally suited for installing a nuclear power plant. The designers decided to equip the aircraft with NK-A engines that would operate on nuclear energy. According to engineers' calculations, such an aircraft could patrol for up to 50 hours or more, which was an unprecedented figure for aviation of that time. Such flight duration provided enormous advantages in anti-submarine operations, as the aircraft could cover vast territories without needing to return to base. The development of the anti-submarine An-22 with a nuclear engine required significant efforts. The NK-14A engines were a new development, and their combination with a nuclear reactor created a series of technical challenges. The main problem was the insufficient power of the engines relative to their mass. The nuclear installation, while providing long-duration operation, was bulky and added significant weight to the aircraft. This affected flight characteristics, particularly speed and maneuverability, which were critically important for an anti-submarine aircraft. To compensate for these shortcomings, Antonov Design Bureau engineers were forced to conduct serious modernization of both the engines and the aircraft's construction itself. The experimental aircraft, designated as An-22 No. 01.06, became the platform for testing the nuclear power plant. This aircraft made 23 flights, and most of them proceeded without serious problems. During testing, engineers tested the stability of the NK-14A engine's operation, the nuclear reactor's impact on onboard systems, and crew safety. As in previous Soviet projects, special attention was paid to radiation protection. A dual-circuit system, similar to that used on the Tu-95LAL, allowed for reducing radiation risks, but completely eliminating them was not possible. Shields designed to protect pilots provided only partial protection, and prolonged radiation exposure remained a problem. The test results of An-22 No. 01.06 were deemed successful. The aircraft proved that a nuclear power plant could operate in flight, and patrol duration indeed reached dozens of hours. This was significant progress compared to previous projects, as the An-22 showed that nuclear energy could have practical application in aviation, especially for specific tasks such as anti-submarine warfare. However, despite these successes, the project encountered serious limitations. First, the NK-14A engines, even after refinement, did not provide the necessary combination of power and mass, which affected the aircraft's overall efficiency. Second, creating and maintaining a nuclear power plant was extremely expensive. In the mid-1970s, when economic problems in the USSR began to intensify, financing such ambitious projects became problematic. After completing the tests, An-22 No. 01.06 was put into storage, and design work continued. Engineers attempted to improve the engines and optimize the design, but these efforts did not lead to serial production. The main reason was that the anti-submarine aircraft with a nuclear reactor proved too complex and expensive compared to other solutions. For example, the development of refueling aircraft allowed conventional aircraft to stay airborne longer, and improvements in radar systems and anti-submarine technologies reduced the need for such exotic machines. Additionally, the risk of an accident involving an aircraft with a nuclear reactor remained significant, making the project less attractive to the military.